All right, so next on the list of things to do, integrals using partial fraction decomposition. Or partial fractions for short. Hit or miss as to how much you did with this in pre-calc? Miss? All right.
Partial fractions.
Oh, it's great. I mean, this is intimidating to look at, but when I tell you that partial fraction decomposition is only really, I mean, if you want to kind of break it down into simple terms, it's getting a common denominator. All right, so you had two fractions, you got a common denominator. In order to combine the two fractions, these integrals are the result of that calculation. All right, but how do you diagnose something as partial fractions? The first thing I do is I take a look at the derivative of the bottom and see if it's a constant multiple of the derivative of the top. In this case, no. I look to see if I can split up the fraction in order to make it something that's recognizable as a rule. If I broke this up as 4x over x squared plus 3x minus 10 plus 41 over the same denominator, you'll be staring at that just like you're staring at this. You're like, okay, now what do I do? Right? So that's your indicator that it's a partial fraction situation. And also, it's a fraction, so you could probably skip over evaluating whether it's integration by parts, because you're really limited to just u substitution or this new concept. All right. Now, this table is actually the best table I could find without actually typing it up myself, which I actively avoid trying to do. But this gives us the sense of the terms in the fraction decomposition. So it's telling us that if I have a factor in the denominator that's linear, this is what one of the terms in the decomposition would look like. Right? If you have a linear factor raised to a power, this is what it would look like. This is very complicated looking, but it's actually very simple. I'll talk about that in a minute. If it's quadratic, then this is what it would look like. But if you really think about it, compare the denominator to the numerator in each case, and you can see that in each case, the numerator has a degree that's one less than the denominator. Right? So when you do your expansion, you're really trying to kind of manufacture a natural log antiderivative.
I hear you say these things like when you're doing your expansion. I don't know if that.
Well, that's the lesson. We're going to get there. So, but at this point, if you look at, if I have a linear function, if I were to take its derivative, the result would be constant, right? Numerator's constant. If I have quadratic and I take the derivative, the numerator is, in this case, linear, which would be the derivative or a derivative of the quadratic denominator. Right? So you're always looking for that difference of one relationship in power. Right? So let's dive into one and see how it plays out. It's actually pretty cool. First step in any of these kind of problems would be factor the bottom if you can. All right? I'm going to leave off the integral and just focus on the fraction. Because as you try some of these problems, you're going to find that it's really just a whole lot of pre-calc and a smidge of calc at the end. All right? Because the idea is to transform the fraction into something that you could work with using integration techniques. Right? So the factors of x squared plus 3x minus 10? Indeed. All right. So we have two linear factors. Here's one, here's the other. My expansion, which is going to be the sum or difference of fractions that are equivalent to the given fraction, is going to contain two linear denominators, two different linear denominators. All right, so I'm looking at x plus 5 and x minus 2. Full disclosure, when I learned about this, when I was in your position, I completely ignored everything the teacher said. And all I tried to do was, through trial and error, come up with numerators that when you get a common denominator would allow for these two fractions to add to this one. It worked like 95% of the time. The problem was that the 5% of the time it didn't work was all on assessments. So that was unfortunate. Worked great when I was doing the homework, worked great in class, but when I sat down to do it on a test, it was like, you chose the one that was really hard to just guess and check. I see what you're doing here. All right. So how do we handle this? Well, we don't just say, well, let me let this be 2 and that be 5 and hope for the best. All right. We're going to solve for those numerators. Now the model up above is telling us that the term in the expansion is going to be a over the linear factor, right? A representing some arbitrary constant, right? So I'm going to let the first numerator be equal to a. Now the second one would also be some a value, some numerator. The issue is I've already used a. So you have two possibilities. You could subscript it, make it a sub 1, a sub 2, or you could choose a different arbitrary constant. You know, maybe let the first one be a and the second one be b. Right? You can choose anything you want as long as they're constant values and not variable components. So no x's in there. This relationship, if I could ever figure out what a sub 1 and a sub 2 are, would give me the 4x plus 41. Right? That's the challenge. So now it's just algebra. The setup is the hardest part with this, conceptually. The rest of it is, well, we got to do the algebra and make it work. So what we're going to do is clear out all our denominators. So I'm going to multiply everything by x plus 5, x minus 2. And so we're going to get an equation, 4x plus 41 is equal to a sub 1 times x minus 2 plus a sub 2 times x plus 5. All right. If you were going to guess and check, you know, multiple choice question, maybe guess and check is an easier way to go. You know, you have finite possibility, only 4 possibilities, 5 possibilities, depending on the assessment. So you look for possible pairings of a values that would give you a 4x when combined, right? But we're going to do it out algebraically because we want to make sure that we have a technique that's going to work in all cases. So we're looking at a sub 1x minus 2a sub 1 plus a sub 2x plus 5a sub 2. We'll be able to come up with a system of linear equations from this because I have 2 terms that contain an x. So I could say a sub 1x plus a sub 2x should be equal to 4x. All right, whatever these 2 coefficients are should allow me to combine these 2 terms to get a 4x. A nice byproduct of that is the x's are going to cancel out, and you'll be left with a sub 1 plus a sub 2 is equal to 4. Now the other part is the constant component. We have negative 2a sub 1 plus 5a sub 2. That's got to equal 41. All right, so system of equations, depending on the part of the exam, the calculator may be off limits. So I'll show you by hand, and then after that I'll show you on the calculator. All right, so I'm going to use elimination. Elimination is definitely the way to go for questions like this. Otherwise you're getting into substitution. And while it seems like it wouldn't be too difficult for 2 variable systems, throw in a 3rd variable, all bets are off. All right, so it becomes a complete time consumer. All right, and you don't want to waste the time doing that. All right, so I'm going to double everything. That's going to get rid of the a sub 1 terms. So I'm looking at 7a sub 2 equals what, 49? And so a sub 2 is equal to 7. And I know that a sub 1 plus a sub 2 should be equal to 4. So I can figure out that a sub 1 has to be negative 3.
Be negative 7. Because then it would be negative 3.
If it's, yeah.
If you got a positive number, a positive number is positive. So
All right, so we have our coefficients, or our constant multiples. And so we could redefine our integral as negative 3 over x plus 5 plus 7 over x minus 2 dx. All right, so all I'm doing is taking the right-hand side of my equation and replacing the a sub 1, a sub 2. This is something you can anti-differentiate. The original was not, right? So what would be the antiderivative of negative 3 over x plus 5? That's part of it. We'll get the coefficient in there first. Negative 3 ln of what? X plus 5. What about the other part?
7 ln
X minus 2 plus c. All right. So definitely was telling the truth. Pre-calc. Little bit of calculus. Teensy tiny little bit. Completely impossible if you don't know the log rules, though, right? Yeah. So if these aren't coming naturally to you yet, add it to your list of things to do. Index cards is definitely the way to go. Little flashcards, they go a long way. That, and I think it's, from what I'm kind of just reflecting on right now, it seems that it's the natural log, the inverse trig functions, and the exponential functions where the base is not e. So like 2 to the x plus 1 or something like that. Those seem to be the ones where I get the most dead air when I ask the question. Like, what is the antiderivative of this? That's where the crickets come in, right? So if you could focus your energy on trying to commit those to memory, then it's going to go a long way. Because most of the basic trig rules, I don't see too many people having trouble with those. Anything that's reverse power rule, obviously you're fine. But those transcendental functions, the logs, exponentials, and the inverse trig, that seems to be where we're having the most difficulty. So make it a point to study those, and it'll go a long way for you. I will show you how to do the solution to a system of equations on the calculator. I'm just debating whether I should show it now or later. You know, let me get through the second example, and then I'll show you how to do both of them on the calculator. It saves you from having to do, you still have to go through the first step here and get it to a point where you have a system, but there's a technique on the calculator that some of you may have learned already, and some of you not. Let me just actually figure this out right now. So AB last year, did you do anything with matrices?
Yeah.
You did? Okay. So then there's a fighting chance that you've seen this before. Does the terms reduced row echelon form sound familiar?
Not at all.
Row reduction?
Oh, yes.
Okay.
Yes.
All right. So
Well, there it is.
the first one was the fancy name for the second
I
one.
remember that. I don't know what it is.
I remember the
Like multiplying rows of a matrix by a number, swapping rows and things like that.
No, we multiplied.
I can remember.
Yeah, we did like multiplication.
Huh.
This is fancy.
Like that rule where if you do like the inverse, you can solve for a system
Yes,
of
we
equations.
did.
Yeah, okay, good. Good. That's going to work. Because this is the foundation of that. That is the foundation of this. All right. But I'm also going to show you a nifty technique that's going to do all the work for you without you having to really do much thinking. All right. But let's talk about the second example. You have quadratic on the top, and it's already written in factored form on the bottom, which is good news. right? But we do have to look at the individual factors. So we're going to rewrite. We're going to focus one factor at a time. We have a linear factor. Linear factors get constant numerators. So that's my a sub 1. Now, I have a linear factor raised to a power here. This is that really weird looking one up above where it has the expansion, like there's like 1,000 terms to it. That's an exaggeration, but it seems that way. What this is telling us to do whenever you're given a power is you start off with the power of 1. So the factor being raised to the power of 1. And then increase consecutively until, oh, I wanted to do that in blue, until you get to the power that the expression is raised to, right? So I have x plus 1 squared. I'm going to start off with x plus 1 to the first. And then I'm going to add to that x plus 1 squared. All right. If this were raised to the 10th power, you would have x plus 1 squared to the third, to the fourth, all the way up to the 10th. All right, that's all that fancy notation up above
You
means.
could just like put them into 3 factors.
It would not work because you need to have a denominator of x plus 1 squared. If you break them up into 3 separate ones, you'll never create the power of 2 out of it. All right. So both of these are linear factors, which means that they get constant numerators, right? So I already used a sub 1, so the next one would be a sub 2, a sub 3. All right, next step in the process is very similar to what we did in the previous one. Well, the step itself, I can't speak for some reason, is exactly the same conceptually. It's just going to play out differently. We're going to multiply everything by x times x plus 1 squared. All right, so we're multiplying by that common denominator that we started with. And when we do that, all the denominators are going to cancel away. We're going to be looking at 5x squared plus 20x plus 6 equals a sub 1 times x plus 1 squared plus a sub 2 times x plus 1 and then a sub 3 times x. All right, in each case, something cancels away from the common factor or common denominator. What's left over, obviously, is whatever the denominator didn't cancel out. All right, so the x canceled out the x, so that's why the a sub 1 gets the x plus 1 squared. In the case of a sub 2, the x plus 1 cancels out one of the x plus 1s. That's why we have these factors and so on. All right. The unfortunate aspect of this is that we have to distribute it all out. You can still try a little guess and check, but it goes sideways very quickly if you're not careful. So a sub 1 times x squared plus 2x plus 1. I'll distribute that in a sec. Plus a sub 2 times x squared plus x, and then a sub 3 stays as is. Distribute. All right, so barring any catastrophic errors in my distributing, this is what the full-blown expansion would look like. Pretty beefy. All right, so what we want to do is organize it in such a way that we can have a system of equations basically anything that's got an x squared has to add to the term that has an x squared. All right, so we have these two guys here. So that's going to lead me to the equation 5x squared equals a sub 1 x squared plus a sub 2 x squared. This is a step that you can skip because in the next step, you're going to drop the x squares and be left with 5 equals a sub 1 plus a sub 2. Okay, so if you wanted to jump right to that, there's nothing wrong with that. We need all the terms that have x's in them. Just bring it here. So that's this one, and this one. So 2x a sub 1 plus a sub 2x plus a sub 3x. I should have written the 21st. I'll do it at the end. Equals 20x. I'm so focused on the expanded form that I neglected the 20x. But anyway, all the x's are going to drop away. So a sub 1, I'm sorry, 2a sub 1 plus a sub 2 plus a sub 3 is equal to 20. The good news in this problem is that you have a lone constant, a sub 1. That has to be equal to whatever the constant is in my quadratic. So a sub 1 has to be equal to 6. All right, so when I do that, you don't need any fancy techniques here because I have a relation between a sub 1 and a sub 2 and 5. If a sub 1 is equal to 6, then a sub 2 has to be negative 1. The other part we have to simplify a little bit, but you can also just play it out in your mind because the 2 times a sub 1 is going to give me a 12. Minus 1 makes it 11. Subtract the 11 from both sides, you get a sub 3 equals 9. So I'm looking at a new integral of 6 over x minus 1 over x plus 1 it was, plus 9 over x plus 1 squared dx. Much, much simpler than what you started with. All right. The first two, very easy. What's the antiderivative of 6 over x? 6 ln of x. Antiderivative of 1 over x plus 1? Exactly. The last one, that's not a natural log, but I could rewrite it as 9 times x plus 1 to the negative second. All right, normally I'd say use substitution, but the inner function has a derivative equal to 1, so I can integrate around it. So I basically just pretend that this is just an ordinary x and figure out what the integral would be. That only works when the inside function has a derivative equal to 1. All right, so in this case, it's going to be negative 9 x plus 1 to the negative first. Let's see. And you can double check. Negative 1 times negative 9 is positive 9. X plus 1 to the negative second. Derivative on the inside is equal to 1. So we have it at this point. But you can see, like, all the work to get us to the point where we could find the antiderivative. Look at all that pre-calc. And you didn't do this in pre-calc?
No, we did.
You did, okay. The thing is, in pre-calc, it's kind of a standalone topic. You spend a little bit of time on it, and then you never come back to it. I mean, I guess that's a lot of things in pre-calc. Here, I mean, it's not too much different because it's like, we'll spend a little bit of time on it, but it could come back repeatedly. Anytime you're given an integral that involves a fraction, this concept could be the way to go. All right, so just something to keep in mind.